Good morning, or good afternoon, or good evening, wherever it is and wherever you are. Greetings and salutations. We are going to continue talking a little bit about quantum mechanics, specifically looking at the Schrodinger equation, which I introduced in the previous video. And so I'm going to take the basically simplest possible model and apply Schrodinger equation to it and see what happens. So before we do that, just a quick reminder, I do have PLC 14 ready to go. I posted that yesterday. It should be active. That's Friday. So that'll be due Friday. And then homework 8 is for Thursday, which is tomorrow. And we'll have a usual quiz there to go along with that. And that will be the last homework set that you will turn in. And I will try my best to catch up and get that graded and back to you. And the homework set that is going to turn up after that will be useful for you to do in order to prep for the final. However, it will not be turned in since I won't be able to get it back to you in a reasonable amount of time, grade-wise. So we will, we'll look at the problems and we can go through and look at those, because they're going to be covering stuff like what we're talking about today and a little bit of what happened yesterday, because this is essentially stuff that's post homework 8. All right, so we'll be looking for doing problems of like normalizing wave functions like I talked about yesterday, and looking at simple potentials and things like that, and then interpreting what the wave functions are and what they're doing. And that's going to be our focus mainly of today. I'm going to do a solving example, and then tomorrow, in tomorrow's video, we will be looking at visualizing what the wave function looks like for different potentials and what kind of characteristics it has. Okay, so let's get back to it. I left off last time talking a little bit about the Schrodinger equation and the way it relates to conservation of energy. Okay, in the sense that when you look at the Schrodinger equation, it looks like this big terrible thing, which it kind of is. But if you think of it as just being part of energy conservation, I was hoping to motivate to you that the terms in the Schrodinger equation are really just related to the idea that the kinetic energy plus the potential energy is equal to the total energy. Now, we had to modify it slightly because and how and why this happens is kind of past the scope of what I'm wanting to talk about in this short amount of time in this class. But effectively, the wave function that describes the wave behavior of the electron or the quantum particle or whatever it is that is under investigation, usually an electron, what we're going to look at is when you see the kinetic energy, it's in the Schrodinger equation, it's going to have it multiplied by that wave function. And then it's going to multiply the potential energy by the wave function and the total energy by the wave function. So you'd think, oh, shouldn't I just cancel those out? No, because it's like it's a slightly different way of looking at the mathematics. What we're doing, I'm just going to give you a quick brief on this. What we're doing in the Schrodinger equation is we're not literally calculating the kinetic energy. We're taking an operator as a way to operate on the wave function to tell us what the kinetic energy is. In other words, the kinetic energy in the Schrodinger equation is this constant, negative h bar squared over 2m, times the second derivative. And then when that thing operates on the wave function, it tells you what the kinetic energy of that wave function is. So you see that when I do something like this, and I put psi here, that second derivative operates on the wave function and tells us, okay, it's this kind of wave function, I multiply by this constant, and that's what gives us the kinetic energy. So you can't cancel this thing in the equation because this is the thing that's telling us what the energies are. Just like you wouldn't want to go into an integration. Suppose I have an integral over here equal to an integral over there. I wouldn't just cancel the integrations, or I wouldn't cancel the stuff that's under the integration sign. Okay, so think about this Schrodinger equation as an application of conservation of energy, but with a few differences in thinking, in the sense that we're considering the kinetic energy operator to be something that operates on the wave function to tell us what the kinetic energy is. And likewise with the potential energy. And then when I add those two things together, I get what the total energy is. And of course, that also has to be multiplied by the wave function. So this looks like plus, I'll do this in here. This looks like plus this thing, which is just the potential energy times, and that's usually, well, that's usually a function of something like x. And then you multiply that by the wave function, but I'm doing the wave function in blue, so let's do that. I'm going to just swap them up, right, like this. And then this is equal to, therefore, the total energy, E, and that's going to be some number that characterizes the total energy of the state that this is in. So what I want to do is show you a little bit about how this works today. By taking the simplest possible potential, one in which it's equal to 0. Or it's equal to infinity. Okay, so what we're going to do today is we're going to set V equal to 0 if we're in a confined range. So let's say we're between x and L, and V is infinity otherwise. What does that look like? Well, let's go here. If I were to graph this potential, what I would see is something that looks like this. All right, so I'm going to graph x here. I'm going to graph x here, and I'm going to graph v as a function of x here. And if v is 0 between 0 and L on the x-axis, then that means between here and here, between here and here, so this is x equal to 0, this is x equal to L, and the potential energy is 0 there. But it's infinity if I'm outside of 0 or outside of L, which means I'm going to get something that looks like this. It goes up to infinity. And this side also goes up to infinity and is out here. Okay, so you think of it as a well or a box with infinitely high sides, such that the particle has to be confined within this 0 to L distance. Okay? We must find the particle in there because it has no possibility of getting out. We have completely destroyed any possibility of it leaving because infinity in here is not going to work. All right? That would mean that if I'm going to have an infinity here, the only way I can change that into anything is to have the wave function be equal to 0. Therefore, the wave function should equal 0 outside of this 0 to L distance. And remember, the probabilities are related to the squares of the wave functions. If the wave function is 0 there, the probability of finding the particle there is also likely 0. Also consequently 0, not likely. It is 0. All right, so we have essentially 3 regions here. I'm going to have region 1, region 2, and region 3. Like so, and I'm going to look at what is the wave function in each of those regions. We just talked about what's happening in regions 1 and 3, so hopefully that should be no trouble for you. I forgot to label this as an example, so let's go ahead and do that now. The name of this potential is, it has a couple of different names, but you can see it would be called something like the infinite square well, or the infinite well. Sometimes we leave off infinite, we just call it the square well. We call it the rigid body, the rigid box problem. We call it particle in a box, particle in a rigid box. It has lots of names, okay? But I'm just gonna call it the infinite square well because I don't know if it's really square. It's really only one dimension. Whatever. The infinite square well. So here what we have then is the Schrödinger equation, which we have to apply to each of the three regions. All right? Can I just call it the SE? The Schrödinger equation? Instead of writing it out every time, Schrödinger equation, to all three regions. Okay, regions 1, 2, and 3. And that means a couple of things. I want the wave function to be continuous. That means that I'm going to have values for psi, the wave function, at all points throughout the entire thing. Okay, this must be a continuous function. And the reason is, that the probability is based off the wave function. Okay, since the probability is based off the wave function, we consider the probability to be an observable and measurable quantity. If we are going to measure something, it had better be continuous. It had better have values at all points that we want to measure it at, because if we're missing one, then that doesn't make sense. All right. Since I do kinetic energy plus potential energy equals total energy, total energy. Since I do this, I've already described a little bit about what happens in regions 1 and 3. So here in regions 1 and 3, we are expecting the wave function to be 0 because the potential is infinity there. Okay, potential energy has gone off to infinity. So wave function goes to 0 in those regions. And therefore, I would consider the wave function to be just a flat 0 line outside of this box. You might think, well, okay, this is all great, but you're talking about measuring quantities. How are you going to construct an actual potential like this? Well, it's possible. Naturally, the infinitely high part is somewhat problematic. So that's not completely physical, but we can make the sides very, very high such that the probability of it leaving is very, very low. It's not possible to technically make it 0 because we can't use infinity. Also, the sides being directly vertical, we can't quite do that, but we can make them sloped. And here's how you do that. What you can do is take an evacuated chamber like this. And it's really important to have bent sides like that. No, it isn't. Okay, like so. And what I'm going to do is I'm going to take plates of metal and put them in here and connect them to a voltage, such that, oh, and by the way, this is an evacuated chamber. Nothing in here. Okay, so I have a, let's make this a grid. I have a grid here and a grid here. Okay, and behind that, I have an electrical plate like so, and I have electric fields here. Okay, such that if a particle that I put in here wanders into this region, I'm going to push it back. the other way. Usually we're talking electrons, so I'm going to have the electric field be pointing away that way in order to make a force that is the other way. This would be E. This would be E, the electric field. If you don't know electric fields, fine, doesn't matter. But the point is that I'm creating a way to force the particle back into the center. Now, is it infinitely high? No. Is it infinitely, does it have basically infinite slope? No. It's got a slight slope to it because there's a potential between the two, between the grid plates, the grid and the second plate here. But nonetheless, the idea is if I now put a particle in here, it will act kind of like this. All right. If you're interested in a little bit more on what these things are, they are known as chronic penny traps. Oh, that's another word for these things, I forgot. The trap. This is called the chronic penny trap. And that kind of approximates what the potential looks like. All right, so in regions 1 and 3, we say we have solved the Schrodinger equation because the only way that we can get anything finite out of that is to have the wave function be identically equal to 0 there, and that means that the particle will never be there. Okay, the question now is what happens in region 2? What I'd kind of like to do is keep another graph available, one that's not a potential graph. So I'll do that a little bit later. All right, so here in region 2, I'm going to apply the Schrodinger equation. And the Schrodinger equation is going to tell me that negative h bar squared over 2m times 2 derivatives of the wave function should equal, because potential is 0, so V equals 0, I've got no potential energy, and that should equal the total energy. That should equal E times the wave function. Okay, now this maybe looks a little bit intimidating, but hopefully not so bad. Let's just write it in a slightly more suggestive manner, in which I take the second derivative of the function, of the wave function, and flop this constant over on this side and say it's equal to negative 2me divided by h bar squared times the function again. And now I'm hoping it looks a little bit more familiar, because this style of differential equation is exactly what you encountered when solving a harmonic oscillator, a simple harmonic oscillator. In other words, we talked about the position and time instead of a wave function in space. So, well, if you recall from 4a, you might know that this negative, say, for example, if it's a spring in a mass system, you might recall that the differential equation for a spring mass oscillator looks like that. And this d, right, this thing here is the acceleration. That's the acceleration of the function of the mass. Okay, and therefore it comes out of Newton's second law, right? Negative kx equals m times a. Solve for a, and you get this. But the point is that these differential equations mathematically look identical. In other words, it's a second derivative of something equaling negative some constant multiplying the function again, right? The very thing I'm taking 2 derivatives of is showing up back here again. Same exact thing here with the x function. What we did with the harmonic oscillators, we found that this is a combination of sines and cosines. Or if you like, it's a bunch of complex exponentials. Either way, because they're equivalent things. Typically, we talk about the complex typically, we don't talk about the complex exponentials, which is sad. But I don't know quite what kind of level of comfort you have with complex exponentials. But if you need to know anything about them, there you go. And this right here is all you need to know. No, that's not 100% true. But the idea then is, okay, so from this then, psi of x must be equal to some some, I'm just going to call it kx plus b times cosine kx. It's a sum of oscillating functions, and those are the sines and cosines. Here I'm just using kx because it's wave-like, and k is a wave number, typically. Okay, yes, I know there's a k here, but that's the spring constant, right? This is the rate of the spring in this hypothetical analogy that I'm making here, so never mind that. The point is that this k comes from the thing that's in the parentheses right there. All right, I'm going to erase this. All right. What do we do now? We've got a wave function whose second derivative equals the function back again, and therefore we know that it must be something like this. Okay. If you were interested in writing it as a complex of exponential, you could do that. It would be, oh, I don't want to use a here because I used a up here. So let's do something different. Let's use something like c plus d e to the minus I kx. So if I was interested in using complex exponentials, it would be the sum of these two things. Nevertheless, we'll stick with the top one here and the sines and the cosines. My point now is I have to figure out how to apply boundary conditions to this. Okay, I should have two boundary conditions. One of them, well, both of them will help make psi a continuous function because we know psi is 0 outside of this region. So let's apply that. We need to now apply boundary conditions in order to make psi a continuous function. We know that psi where x is equal to 0 should equal 0, and we know that where psi at x equal to L should also equal 0. Because as soon as we're outside of the well, the wave function is 0 everywhere, which means that whatever I'm doing inside the well has to connect to the zeros, okay? If I apply these two, all right, let's take the first one and say x equal to 0 has to be 0. Let's take this one and say that, I'm going to say that psi of x equal to 0 should equal a times the sine of kx, which is 0, plus b times the cosine of kx, which is also 0, and that should equal 0. The problem here is that the sine will be 0. The sine of 0 is 0. So this is not a problem. This, however, is a problem because the cosine of 0 is not 0, it's 1. Therefore, this is telling me that b is going to be 0. Right away, I have to see that's equal to 0 because the cosine of 0 is some number. Okay? So that's part of it. The second part down here, where psi of x equal to L, I'm going to do the same thing now. I don't have to worry about the cosine component because the cosine component does not go to 0, right? At the two endpoints, it won't be 0 because the cosine starts at x equal to 0 or theta equals 0, whatever you like, at 1 and makes a full cycle and ends at 1. It will not be 0 at the endpoints. It could be 0 in the middles, but then it's back to being a sine. All right, so this term is automatically eliminated because its coefficient is 0. Now I only need to worry about what the a term is doing with the sine in it. Now I'm going to use a times sine of kx, which is now k times L, and say that that's equal to 0. Now, at this point I have a couple of options. I have the option of saying, well, sine KL could be 0, or A could be 0. If I set A equal to 0, I don't have a problem. Or let's call that the trivial solution to the problem. That's the one in which the wave function is zero everywhere and I don't even have a particle in there. This is the not useful solution. Let's suppose then that A is not zero, and therefore the sign of KL is going to be the thing that's zero. If the sign of KL is going to be zero, then we know already that K times L must equal some integer multiplying pi. Because the sign of pi, sign of 2 pi, 3 pi, 4 pi, whatever you like, that's going to be zero. So KL has to be some integer number multiplying pi, and therefore K, whatever this is, has got to be n times pi divided by L. Notice, however, that we have immediate restrictions on this, okay? This is a situation where n could equal 1, 2, 3, etc. Okay? If it's equal to 0, that's not useful in that sense. K being 0 isn't useful. So we're going to say that n is equal to 1, 2, and 3, which means K has only specific values that it can take on. All right? So if we look at that, then I take a look at what the K constant is from back here. All right? I'm going to go take a look at what happened to, how did I write sine kx from over here? What is K really? Well, I had to take two derivatives of this thing and get it back. So let's plug, why don't we just check that this is an actual solution to the Schrodinger equation and plug it back in. If I do that, what will happen is that I will take two derivatives of it according to the Schrodinger equation and the kinetic energy operator. And I'll say that that has to equal this constant multiplying the wave function back again. All right, so let's do a quick check here. If psi is equal to A times sine kx, does that satisfy the Schrodinger equation? I mean, it should, but let's do this. Two derivatives of that. Okay, if I take two derivatives of this, I'm going to get, the first one's going to give me K out and then A times cosine. And then I'm going to do another derivative of the cosine that's going to flip it back to negative of the sine. So I'm going to get negative. I'm going to get 2 powers of K out because I did two derivatives. I'm going to get A sine kx back again. If you look carefully at that, you'll notice that that's equal to negative K squared times psi again. And therefore, if I now compare it to this thing over here, I've got the negative sign here and the negative sign here. Therefore, the K squared must be whatever's in parentheses over here. That means I can now deduce that K is equal to the square root of 2me divided by h bar squared. Alrighty. However, K, we now know, has restrictions on it, and it's this. So K is equal to that, and by analysis of the wave function from the boundary conditions, this is equal to n times pi over L. Okay. So we're getting close. We're getting close. Our goal here, I guess I should have mentioned this in the beginning. Our goal here is to find the wave functions that describe the wave, I did mention that describe the wave properties of the electron. Also, our goal is to find the total energies that that electron can have. But notice what's happening. I now have an expression here for this K thing in two ways. Now, L is just the length of the well, or the width of the well. N and pi are just constants. H bar squared and 2m are characteristic constants. So really, I can solve this equation right here for E and get out what the energy spectrum is going to look like. Now notice, this is very interesting. We had to put restrictions on the k times L in order to make it 0 because the sign oscillates and it's only 0 at certain points. We had to pick those points out. That means that the energy can only have certain values, and we have to pick those values out based on the n pi over L. So let's solve this for E, and that's going to give me the spectrum of energies, just like we found with the Bohr hydrogen model. We found that the energies were negative 13.6 electron volts divided by n squareds. We're going to come out with the spectrum of energies here. We're going to solve that for E. If I do that, I'm going to square both sides to get rid of the radical, and then just pop the h bar squared over 2m to this side. Okay, so E, which now can be thought of as a function of the quantum number, n, is going to be all of that stuff squared and then multiplied by this stuff. So it's h bar squared times pi squared divided by 2m L squared, and now I got the index, which I'm going to put on the very end out here, n squared, like that. So this is how we calculate the energies that are allowed in the square well. Notice that there is not a continuous function of energies here. Just like in the Bohr atom, where the energies were quantized as, like I said, 13.6 electron volts divided by n squared. This is some number here multiplied by n squared, but n can only take on integer values, 1, 2, 3, because we looked at it and said that's what the sign is permitting. All right? So this is our first real exploration of, here is a situation in which, like the Bohr hydrogen model, the electron can only take on certain values of energies because there are only certain places where it can have a wave function that satisfies the boundary conditions. The wave function of the electron has only certain shapes to it. It can't be anything. And because it has only certain shapes to it, it can have only certain energies associated with those shapes. Okay, so this, where n is equal to 1, 2, 3, ... tells us that we have some multiple of this number in parentheses times n squared. And that n squared is known as the principal quantum number. Well, I can't spell. Actually, it's the pen. The pen can't spell. It's not my fault. I was meant to write principal quantum number. Principal quantum number. Okay, there we go. Okay. Good. Excellent. Now that we've found the energy spectrums, let's go back and look at the wave functions. And then we'll take a look at visually representing all of these things. Now the wave function as a function of x was a times the sine of kx, right? And k is this thing, square root of 2me over h bar squared x. And e is a function of little n. And that means that this psi also has the index of n underneath it, so I have to pick which energy I'm interested in and therefore figure out what the wave function for that energy looks like. All right. The first thing that comes to mind here is that we don't know the constant A, and it would be nice to know the constant A. So let's look at it this way. I know that the particle must be confined within the 0 to L distance. It will not be found outside of that. Therefore, I should have a 100% probability of finding the particle within 0 to L. And that means I'm going to normalize this. So let's go through the normalization process. In order to try and find out what the A constant is. So normalization means, typically, what I wrote yesterday, was that I take the square of the wave function multiplied by a little distance during which I want to find the probability, and then I add all those probabilities up. Okay, so I take psi of x, I'm going to square that. I'm going to multiply by the width of the piece that I'm interested in finding. That's going to give me a probability. I'm now summing all these probabilities. That should equal 1 because I'm going from minus infinity to plus infinity, and yeah, I can't really do better than that in terms of going everywhere. Here, in this situation though, remember that outside of 0, to the left of 0, on the way to minus infinity, the wave function is 0 there. And that means the probability is 0 there. So I can go and add up a bunch of zeros from minus infinity all the way to x equals 0. I will be adding up zeros the entire way. Likewise, past the distance L, from L out to positive infinity, I will be adding zeros. Psi is 0 there, so there's no point in adding a bunch of zeros. I'm just going to concentrate on the part where I know the particle must be, and that's going to mean I'm integrating from 0 to L of this sine of psi squared dx, and that's going to equal 1 because everything else is 0. Okay? So let's go ahead and do that. We will then be able to find the constant A through this process. Okay, what we're going to do then is we're going to take psi squared and integrate like this. So we're going to get A squared integration 0 to L of sine squared, all of this stuff, which I'm just going to call K again. I'm going to call Kx dx, and that's got to equal 1. Let's see, is that it? That's it. All I got to do is that integration. Okay, so if I do that and I integrate the sine squared, this is great practice for those of you who are proficient at integrating by parts, because you can break that up into that type of thing. But let's go ahead and do this. This integration then of a squared, when I integrate this thing here, it turns into, let's see here, what does it turn into? It's going to turn into, if I remember, x over L minus 1 over pi kx over L times sine kx cos kx. Is that right? Something like that. Such that when I do this and I evaluate this between 0 and L, I'm going to evaluate that between 0 and L. You can see right away that when I evaluate it at 0, I'm going to get 0, because the 0 is going to go to the x part here, and the sine of 0 is going to kill this part off, so the 0 term is already 0. Then we're going to look at the L term, and we're going to look at that and say that it's a sine of KL and a cosine of KL. Don't like that. Minus 1 over pi times those two things. I wonder if I got that. So what we're going to do is we're going to have a squared times x over L. L, it should be L over L. Sorry. I'm evaluating x equal to L, so this is L divided by L, minus 1 over pi times sine of KL and cosine of KL, like that. Okay. Well, we know what K is. Remember that K is the n pi over L thing, okay? So what we're going to get here is sine, this is going to be a squared times the sine 1 minus 1 over pi, sine of n pi, cosine of n pi. Okay, like so. And the sine of n pi is just 0. So that's no problem. I think I'm missing something here. What am I missing? If I put in 0 for that, it's going to be 0. Yeah, so that's 0 minus 0. L. I'm missing something. So I probably got the integration wrong. Somehow. Because I know what this is supposed to turn out to be. And this is equal to 1, by the way. Which means this is 0. And so it looks like a squared is 1, but it's x over L. Maybe that's the problem. Maybe it's just x and there isn't that x and the pi in there. Well, I'm just trying to guess a little bit of what this looks like. But nonetheless, I know for a fact that I messed something up, but I don't quite remember. I got that integral wrong. But the point is, so this is ... wrong. ... I got the integral wrong somehow, because I know that a is supposed to turn out to be the square root of 2 divided by L. Is what I want. It's what we want. It's not just about what I want, it's what we want. So whatever it was, I messed that integral up, so obviously I don't remember what it is, but I do know that this is right. I should get that the constant is square root of 2 over L, so that when I go back and look at the wave function, I can use, instead of a, I got square root of 2 over L here. Like that. Now notice something interesting, okay? Quick unit check. How do I know it's got to have a square root of L in the denominator? Well, because the units have to work out as 1 over the square root units of the length. Why? Because when I look at this thing here, that kind of defines what the units of the wave function have to be. If I square the wave function and then multiply by a length, I should get no units. In other words, if I square the wave function and multiply by a length, that should make it dimensionless. And that's why you know you have to have a square root of L in the bottom. All right? So I know it's that. Sorry, I messed something up. Maybe that's like a 1/2 or an L. So I messed up the constant somehow. Anyway, sorry about that. Let's start by plotting both the wave function and the energy levels. Because now I'd say that we've pretty much solved the whole thing mathematically, let's look at what we have and interpret as we do. Okay. Okay, so let's plot psi of x and e sub n. Now that means that I'm going to take the wave function here like this. This is my x-axis, and here is 0, x equal to 0, and here is x equal to L. And I have wave functions to plot between those two. After those two, after this point, we already know the wave function is 0. So the wave function being 0 would be going out like that, and would be going out like that. We already know that psi is 0 outside of that. If I look at the very first, if I choose n equal to 1, choosing n equal to 1 here makes this thing equal to 1. And ultimately it just becomes sine of all this stuff. In other words, this kx, right? This kx here, that is k, and this is equal to n pi over L. So really what you're doing is you're plotting n pi times x over L. And that means that when n is equal to 1, I'm plotting pi times x over L. And it's a sine of that. Such that, I'm going to need to use this. That was all wrong anyway, so never mind about that. If I take psi of 1 here, it's going to be square root 2 over L times the sine of n of 1 times pi x over L. What that means is, if x is equal to 0, then the function is 0. If x equals L, then sine of pi is also 0. And when when x is L over 2, then this is the sine of pi over 2. That means it's reached a maximum in the middle, and it's 0 on either side. So therefore, at L over 2, it should be reaching a maximum, say, maybe the maximum is there, and so it looks like this. Right? This is the n equal to 1 state. Just what I call the jump rope state, right? And now it's flopping up and down like this. Okay, exactly like a jump rope would do. What is the energy of the n equals 1 state? So the energy of 1 is equal to h bar squared pi squared divided by 2m L squared times n squared, but that's just 1, so it's just equal to this. Alrighty, so the energy of this state is that much, and this is called the ground state. If I move to the n equals 2 state, what does that look like? Well, it's the next most energetic sign, which has to have 0 as its boundaries. So what's the next thing that's a sign that I can fit in here? Well, it's going to have to look like this. When I go to psi 2, we can just look at it really quickly here. That's square root 2 over L sine 2 pi x over L, such that x is 0 in L, so it's 0. At the halfway point, when x is L over 2, now L over 2 get canceled with 2 over L, so now I get sine of pi, but that means it's equal to 0. So what I get for this then is this type of thing. So if I go to x equals pi, L over 4, right? Where x equals L over 4, that's where it should be peaking. That's right here, L over 4, and it should be reaching 0 there, and it'll peak again here at 3L over 4, but in the opposite direction. Okay, so what I'm going to get then is one that looks kind of like this, right? And this is the n equals 2 state. It's the next sign that is going to fit there, and then its energy, E2, is equal to 4E1 because of the n squared. Okay, so a couple of things to come away from this, with which to come away from this. When I'm increasing energy, then I'm increasing the number of peaks in the wave function. Remember, or peaks or valleys if you like, okay? So remember that with the n equals 1 state, I've got 1 peak. With the n equals 2 state, I've got 2 peaks. You see the trend here? If I go to the 3 state, I'm gonna have 3 peaks. 4 is 4 peaks, 5 is 5 peaks, okay? Notice also that this has to rigorously achieve a 0 here at the boundaries, okay? There's no fooling around with that because we know the wave function must be 0 outside of that, and the wave function must be continuous. Therefore, it has to come straight down to 0. This is why the cosine term would not work. Okay? Lastly, let's take a quick look at what the energy values look like. If I plot the energy values, okay, and I make a plot like I did with the Bohr values, I'm going to get a ground state down here, E1, and then the next allowed energy state is 4 times as high up, so let's just say it's like here, E2, and then the next one is 9 times further up than E1, so it's way up here, here's E3, and the next one is 16 E1s, right, so it goes way up there. The spacing is increasing as you go up. Which is opposite to what the Bohr model was, right? We went up from 1 to 2 to 3 to 4 to 5, but we found the spacing decreased every time. In this one, the spacing is increasing every time. Okay, let's underneath this, let's look at a probability, right? In other words, I'm going to think about squaring the wave function and plotting it versus x, okay? So here, in the n equals 1 state, if I square the wave function, nothing earth-shattering happening. It's 0 at the sides and it's kind of peaked a little bit more in the middle. Okay? So if I just go to the same boundaries here and here, then my n equals 1 might look like this. Okay? And of course it's 0 outside of that because the wave function is 0 outside of that. Now, let's take a look at what happens at the n equals 2 state. If I look at the n equals 2 state, I'm going to square this thing. That's going to make this positive, so it's going to flip it up. So the n equals 2 state is going to look something like, this. Like so. That's the n equals 2 state. Notice what's happening here. This is the probability, okay? So what's the probability if I put a detector directly in the middle of the well? If it's in the n equals 2 state, I will not detect it there because the probability is 0 here. It crosses, the wave function crosses the 0 line in the halfway point. At the halfway point, if I put a detector there, I should never find the particle there. This is interesting. That means it's going to be confined either this side or this side. Well, not confined. It'll be found over here or over here, but not right in the middle, which is kind of a strange thing, okay? So as you go up in wave function, you'll find the same thing because the 3 state will cross twice, and then there'll be a peak here, a 0, a peak here, 0, and then a peak here. So every odd wave function has a peak at L over 2, and every even one has a 0 at L over 2. That's one way to figure out if you're in an even or an odd state. Put the detector right at the halfway point. If you get something, you're not in an even quantum state. Okay, let's now go through and pop a few numbers at this and take a look to see what would it look like energy-wise if I was asking what's the spectrum, right? We looked at the Bohr energy drops of an electron. As we excited the electron up to higher and higher energy levels and dropped it, it emitted light, okay? So as we excite an electron up and further up in these energy levels and it drops, what kind of wavelengths are we going to be talking about? Right? So suppose I excite an electron up to the 3 state and it could drop to the 2 state and emit a photon, which I'll just call gamma. Or, of course, it could also drop all the way down here and emit another photon, a different gamma, one of higher energy, okay? And the 2 could drop to the 1, but now I've got a really busy diagram, but never mind that. Okay, so let's take a look and put a few numbers in and see what we come up with here, okay? This is done. All right, so suppose that I'm looking for these wavelengths. What is the spectrum? Okay, so what kind of wavelengths am I looking at here? Well, remember that the energies of the electrons, or the energies of the electron, when you look at the different levels, you subtract those, and that's the energy of the photon that would be emitted between those two levels, okay? So let's just take the easiest one first. I didn't draw it here, of course, but let's just take the 2 to 1 drop. Remember that when I think of the energy of the electron, the negative of that is equal to the energy of the photon that's emitted. So if I think about, I have an electron in the 2 state, an electron that drops from the 2 state to the ground state, it emits a photon. We can calculate its energy now because we know the energy spectrum of the electrons in the infinite well here. What that means is, dropping from 2 to 1, then my delta E of the electron is going to equal 3E1, right? It started, well, it's negative 3E1, but its magnitude is 3, right? Because this is 4 of those, and I'm subtracting 1. So the loss of energy of the electron is negative 3E1. So that should equal the negative of the photon energy. So you can get rid of these minus signs. I'll be able to know what 3 times E1 is, and I'll be able to then set that equal to hc over lambda. This is the 2 to 1 transition of lambda. Okay. I'm gonna have to start erasing this now. Okay. All right, so this is the 2 to 1 transition. So the hc over lambda is the energy of the emitted photon. I can solve for that. Lambda 2,1 is then equal to, all I have to do is basically flip-flop those two things and say that's equal to hc divided by 3e1. So let's go through and look at what that means. hc over 3e1, and this is all of e1 right here. So this is h bar squared pi squared over 2ml squared. Ding, ding. All right. Well, what are you going to do? Well, the first thing you can do, if you like, is deal with the h bar. Because I've got an h up here and an h bar down here. Okay, fine. So what do you want to do? Do you want to make them both h bars, or do you want to make them both h's? Some of them are going away here. At least one of them is going away top, right, with the bottom one. So if I make this an h bar up here, What's that going to do? Let's try that. Let's going to make that 2 pi times h bar c divided by 3 times h bar squared pi squared. And then I'm going to flip this denominator up to the top. So I'm going to multiply by 2ml squared. Okay, so that means I can get rid of an h bar and a pi here and here. I've got a 2 multiplying a 2, I've got an m which is here, I've got a c, I've got an L squared. All right, so the energy of the wavelength of the photon is 4/3 mc L squared over pi h bar. We'll just work with that a little bit more. What did I say it was? 4/3 mc L squared divided by h bar pi. Okay, let's work with it a little bit more. I am now going to put in h over 2 pi for this thing. That means I'm going to cancel that pi away here and here. I have an h which has a 2 underneath it, so I can flip the 2 up top. So I'm going to flip the 2 up top, now that becomes an 8. I have an mc L squared divided by h. And so what I can do is play the usual fun game of multiply top and bottom by c. So I'm going to multiply top and bottom by c, and that's going to give me mc squared, which is useful, and hc, which is a constant we know. And I forgot the 3. There we go. All right, so this is what the wavelength of the photon would look like that would be emitted. Given an L squared, we can calculate what this is. All right, so let's calculate what this is. So let's assume an L. Let's suppose L is small. Maybe it's a nanometer. Okay, let's suppose L is 1 nanometer. Let's evaluate this for L equal to 1 nanometer. The wavelength of the 2 to 1 transition then is, this is 1 nanometer squared. This is going to be 8/3. mc squared, this is an electron dropping, so it's 0.511 MeVs. Which means it's, let's do 5, I can't, I just got to do 0.511 times 10 to the 6th electron volts, okay, times 1 nanometer, that is squared. I'm going to divide that by 1240, 1240 EV nanometers. All right, so let's take a look. If I do this, quick unit check tells me that the EVs are going to drop away. One of the nanometers is going to drop away, leaving the other one, which is good news, because this, after all, is a wavelength that I'm looking for. And so I'm going to get a number from this, which is, actually, I don't know what this number is. Let's calculate it really quickly. Calculator. So I got to do 8 divided by 3. I got to multiply that by 0.511. Oops. E, where's my E button? There it is. Nope, that's not it. That was other E. Normally it's right there. Oh, that's weird. All right, well, whatever, 0.511, and I'm going to multiply by 1. I'm going to divide that by 1240. And now I need to multiply that by 10 to the 6th. So that's 1, 2, 3, 4, 5, 6. So this looks like 1090. I'm getting 1098, 1099, so about 1100. Oh, yeah, I multiplied by 8/3. So this is about 1100 nanometers. I'll put a question mark there just in case I screwed something up. 1100 nanometers. So that's well into the infrared, okay? You could also calculate the 3 to 2 drop. That would be, however, the 3 to 2 drop, E3 would be 9 E1s. And therefore this energy difference would be 5, right? 9 minus 4 E1s, that would be 5 E1s. So where would that come in? That would come in here with the 3, right? So I'd have a larger energy drop, which means that my photon would be smaller. Okay, that means this would change to a 5, is that right? I think so. If this was the 3 to 2 transition, this would be a 5. And then I would have 8/5 instead of 8/3. If this was the 3 to 1 transition, I would get 9 minus 1, which gives me an 8. That's even better, because instead of 3, I'd have an 8 here. That would completely destroy this number, and that would mean I get just that, and I would take 3/8 of that number, and that would probably be something in the visible spectrum. Let's just see. Times 3 divided by 8 is 1, 2, 3, 4, 5, 6, 412. So if I do the 3 to 1 transition, that's a 412 nanometers, which is blue. Okay? Oh, that's kind of cool. So that's how you can figure out the spectrum. All right. Remember that you're always when you're talking about the emission spectrum, you're always pushing the electron as far up as you can, and then having it go down, 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 and jump down, jump down, jump down, emit a photon every time. Okay. The only way you can get it to jump back up is if you take those photons and you emit them back in there. Note, however, that if I had a photon jump from 3 to 2 and it emitted a photon, I could grab that photon. In the time in the time that I got that photon, it jumped from 2 to 1. Now it's in its ground state. If I take the 3 to 2 photon and I push it back at it, it will not absorb that photon because that photon has a wrong energy. The only photons that it can absorb here are going to be ones that will put it to the 2 state or the 3 state or the 4 state. If I give it a photon of the 3 to 2 transition, that's not going to have the right energy to pop it into the 2 or the 3 state, right? Notice this is an energy of 5 E1s. To get to here, I need 3 E1s. To get to there, I need 8 E1s. So a 5 E1 is going to put me somewhere up here. It's not going to, it can't have that. So it's transparent then, if it's in its ground state, to those energy photons. Okay, cool. I got a couple other things I really kind of want to do here, and that seems like it's okay. We got a couple of minutes left. Let's go ahead and give this a look. What I'd like to do is take a look at what the uncertainty principle tells us about this. What does the uncertainty principle tell us about this? So let's take a look. The uncertainty principle, we know what it looks like in terms of momentum, in terms of momentum and position. Because we have a confined particle, right? This is a confined particle, and therefore we have an uncertainty in the position. Note that whenever you have a confined particle, your uncertainty in the position is essentially the size of the confinement. I was talking about the dust particle in the 10 micron tube last time, and you'd say, well, the dust particle's in there somewhere, so your uncertainty in its position is basically the size of the tube. The same thing is happening here. I've got a well. I don't know where it is, but my uncertainty in the position should be about the size of the well. So the confined particle has a delta x, which is approximately equal to L. That means that when I look at the uncertainty principle, delta P at the minimum, right? So let me just say this is minimum here. At the minimum, this is 1/2 h bar, right? So I've got an h bar over 2L here. That's giving me a minimum uncertainty in the momentum of it. And therefore, I have a minimum in the uncertainty in the speed of it. That means that a confined particle basically can never be at rest. because you're always, at the minimum, you're always uncertain to a particular degree. Now, if you were thinking, hey, I've got this particle, it's confined in the box and it's sitting at rest in the ground state, it would have an uncertainty in its momentum of at least this much, which means its momentum is about possibly that much. Okay. Note that this is like 1/2 h over L, no, whoops, sorry, wrong thing. I did the wrong thing here. Sorry, this is equal to h over lambda, there we go, h over lambda, and therefore this is true when lambda is h over lambda is h bar. So I've got a bar missing here, it says h bar, so I've got a 2 pi missing here. Let's do this, 2 pi. I need a 2 pi up there. So this is the same as having a wavelength in which it's about equal to 2L, right? Lambda is about equal to 2L of the, inside the well. And that's exactly the same thing as what happened as our ground state turned out to be, right? So our ground state had a wavelength of 2L because it had a half wavelength in L, which means the second half of it was in the next L, so that's 2L long. Now, I'm off here with a little 2 pi and stuff because of the h bar, but honestly, the idea behind h bar and the 2 pi, it's not that big of a deal. So you'd say that the wavelength is about that, and that's what it was. So the ground state, this is satisfying the bare minimum of the uncertainty principle, right? So it is working out from that perspective. That's one thing. I wanted to point out that when you have a confined particle, like I said, you will never find a confined particle at rest. In other words, there's always a minimum energy in it, and that was what we called the ground state energy, right? The ground state energy wasn't zero, it was h bar squared, pi squared over 2, whatever that stuff was. Therefore, it always has that as its kinetic energy, because its potential energy was zero in our infinite square well case. And therefore, it's always moving around a little bit. And this is basically true of every confined particle. When it's confined, it's always doing something. You're uncertain as to what it's doing because you're uncertain in its velocity and you're uncertain in its momentum, but you're always thinking of, look, if it's at rest, it's only at rest for a split, it's for basically no time, and then it's moving on to do something else, okay? So it always has a minimum in the uncertainty in the momentum, which means it's basically always moving. So you cannot confine a particle and then expect it to find it at rest. All right, that's like confining dogs. You can't, or a tiger. You can't expect to see it at rest. Well, I guess you can actually. Dogs do sleep a lot. All right, so there's that part. Looking at the uncertainty. Last piece I want to put in here is finding total probabilities. Finding total probabilities. Actually, I think maybe this is a little bit too much for today if I do that. I want to just mention, I want to find total probabilities. We normalized the wave function. So I could ask the question, what's the probability of finding the particle in its ground state between, I erased my wave functions, but between a certain range. Now, we know that between 0 and L, there's a 100% chance of finding it. But what if I took a smaller range? What if I asked, what is the probability in a narrow region around this much, right? Maybe it's around 1/4 L, or 3/4 L, or half L, or something like that, right? So this is going to involve taking squares of the wave function and multiplying by whatever those widths of the strips are. And as long as the strips are small enough, you can get away with this approximation, right? This is an approximation, but you can get away with it as long as this is a small number, right? This is small. All right, so we can do that. However, the integral way of doing it, we'll touch on that next time. and then I'll go and calculate a little bit more on the probabilities if you divide it up into small squares, and then I'll look at doing it for a larger region. That's a case where you do have to do the integration and sum them all up. So we'll pick up with that on in class starting next time. Alrighty? So enjoy the rest of your day and take a look at that homework and be ready. We'll submit that tomorrow and we'll have a quiz tomorrow. Alrighty? So see you next time, folks.